and welcome to this video. In this video we're going to be going through the topic of refraction. So this is going to refer back to a lot of the GCSE content that you would have done in physics. You should already be familiar with the idea of what refraction is. All we're going to do is recap it and then add a little bit extra information, but hopefully this topic should be fairly straightforward as long as you understood it in GCSE. So in GCSE you would have learned that refraction is when light changes direction when entering a new medium. Entering a new medium, and we could also add this is due to a change in speed. Okay, so if we imagine we were looking back at imagine a boundary between air and then glass. So this is the air from outside and this is the glass on your window. If we imagine that light comes in at some angle, we can then draw this line here, which we would refer to as the normal. The normal is basically just there so that it can make a few things a little bit easier for us, so for geometry purposes essentially. And we know that if the light is coming in and it's going to go into glass, glass is obviously more dense than air, so we know the light is going to slow down, and if the light slows down it's going to then bend towards the normal here, okay? And this would be θ1 and this would be θ2. Now this general explanation will work, but let me just explain in a bit more detail why this happens. And to do that I'm gonna have a much larger diagram just to be able to really depict what's going on here. Okay, so we now have the wave coming in this direction, and let's draw a top-down view. We have some wavefronts, okay, and these are all going to be traveling at the same speed while we're in air because it's in the same medium, so there's no change in speed. But as soon as we go to glass, when light enters a more dense medium, we're going to get rid of this term more dense and we're going to have to refer to it as more optically dense medium. So when light enters a more optically dense medium, it starts to slow down. But if you notice here, this side of the wave here is going to enter the more optically dense medium before the other side is, and this side is going to start to slow down while the other side continues to speed up. And so it's almost the same as having a tire stuck in some mud while the other half of your car is on tarmac. If you then accelerate, your car is just going to skid around and then change direction in the mud, and then you're going to get this whole wave traveling in a new direction, okay? And the wave will be much slower. Okay, so the wave slows down. So the wave slows down when entering a more optically dense medium. Okay. So hopefully this explains why this changes. But if we know the speed is decreasing and we know the wave speed is equal to the frequency times the wavelength, if the speed is decreasing, surely the frequency or the wavelength has to be decreasing also. So how do we know which one it's going to be? I've purposely drawn this to try and give away some hints. We know the distance between these is going to be the wavelength, and so the wavelength actually decreases. Okay, so let's write this explicitly. So this is because the wavelength decreases frequency will stay the same. Frequency is the constant because the frequency of the wave is only dependent on the source of the wave. So if the source of the wave is a laser, it's probably going to have quite a high frequency. It's just an LED light bulb, or any other monochromatic source of light. It would have a little bit of a lower frequency. But even such, the frequency is dependent on the source of the wave. The wavelength is dependent on what medium it's traveling through. So the wavelength can change. Another example of wavelength changing would be redshift, which you might have also met at GCSE. Now, this is what happens when we're entering a less dense medium. Let's also look at what happens when we're entering a more dense medium. Let's also look at what happens when we enter a less dense medium. Okay, so if we were to go the other way and have this boundary here as glass, so we're starting inside the glass and we're trying to travel to air, then we know as it comes in, it's going to speed up, and so it speeds away from the normal. Okay, and this is θ1, and this is θ2. This is the normal. There we go. Okay, now it speeds up because it's entering a less optically dense medium, so the wave speeds up when entering a less optically dense medium. Okay, and that is, if we were to think about this in the terms of all of the wavefronts, this side of the wavefront is now going to speed up. So it's almost like you're driving through mud, and now one of your wheels hits the road. That's going to start to take off, and then you're going to change this here. It's also worth noting that if the speed is increasing, it's the wavelength is increasing also. Okay, it's not the frequency that's increasing, just the wavelength. Okay, now we can think, how do we put numbers on optical density? Because all of physics means that we're going to have to take some concept and reduce it down to just numbers so that we can work stuff out and predict what things are going to behave like. So how do we put numbers on optical density? Well, that is called the refractive index. Okay, now the refractive index of something is basically just a ratio. So it's a ratio of light to the speed of light in the substance. Okay, whatever that substance might be. It might be air, it might be water, oil. These tend to be the common materials that they'll give you. And so the ratio of the speed of light in a vacuum to the speed of light in a substance, we've basically chosen here the speed of light in a vacuum to be our set 0 point that we can compare everything else to. Now, the reason we've done that is because we know the speed of light in a vacuum is constant. It's never going to change. The speed of light through a substance is going to change very slightly if we heat that substance up or cool it down. Doesn't matter the temperature of a vacuum, it's always going to travel at the same speed. So our equation for the refractive index is therefore just n, the refractive index we refer to as n, is c, i.e. the speed of light in a vacuum, over cs, which is the speed of light through the substance. Now the speed of light through a vacuum is a constant on your formula sheet. It's 3 times 10 to the 8 meters per second. Okay, because this speed of light through the substance can only reach a maximum value of being c, the minimum value that this possible refractive index can be is 1. Okay, so a refractive index has a minimum value which is 1. That's because if we were to think about it, if we have a very large number on the top and then the speed of light through the substance is smaller than that, we have a top every fraction, so we're going to get 1 point something, or even 2 point something. But then the maximum value that the speed of light through the substance can be is 3 times 10 to the 8, meaning that our refractive index has a minimum value of 1. It's the smallest it could be. This is true for a vacuum, but it's also true for air. So the only refractive index you actually have to know is that the refractive index of air, so refractive index of air, which you'll sometimes just see written as n subscript air, is equal to 1. Okay, this is something you have to know. Now you might say, well, if that's true, surely then air is a vacuum. This isn't true. Okay, technically this is 1-to-1 significant figure. If we were to do this, if we were to round this to a more appropriate degree of accuracy, it would be more like 1.0033. Okay, so it's a much smaller value. It is very close to being a vacuum, which is why we can approximate it to be a vacuum, but it's not an exact vacuum. Okay, but for the purpose of calculations, it just makes everything easier if we just call it 1 rather than having this extra 0.003. Okay, so now we can kind of assume that if this is the refractive index, it's going to be a measure of how much the thing is going to speed up or slow down as something begins to change medium. And if it's a measure of how much something is going to speed up and slow down, it's going to be related to the difference in these angles, okay? And that is called Snell's law. Okay, so Snell's law is how we are going to quantify what the angles should be depending on what the refractive indices are. So just to put this into perspective, if this substance here has a refractive index of n1 and this substance here is n2, when the wave comes in, it forms an angle that we call θ1, and then it's going to refract with an angle called θ2. Okay, and the relationship is that n1 sine θ1 must be equal to n2 sine θ2. Now again, the derivation of Snell's law is not something you have to know, so if anyone's not interested in it, don't worry, because you don't have to know it. But if anyone is interested, it's fairly straightforward as long as you're able to differentiate something using the chain rule. Okay, so if you wanted to look at that, I would recommend going on hyperphysics. Hyperphysics has quite a good, very short derivation of it that's quite simple. Again, as long as you know how to differentiate. If not, I wouldn't worry too much about this. But you do have to know this equation and you have to be able to use it. Now, this equation is, if anything, the most important equation that you have to know for refraction, because you'll find that all of the subsequent equations that come from this, so when we're working out the critical angle, which is what we're going to have a look at now, and so forth, they're all derived from Snell's law. So Snell's law is the most important equation to know for refraction. Obviously it's in your formula sheet, so you don't have to memorize it, but I always say it's never a good approach to just say it's in the formula sheet so I don't have to know it. You do have to know it, you just don't have to memorize it. So this is Snell's law. Now you can use this and basically just rearrange to find out basically anything. You could find out the refractive index of the second thing. You can find out what angle you're going in at or coming out at, as long as you know all of the other information. So applying Snell's law is never going to be too difficult. The difficulty might come in when we start talking about the critical angle. Okay, so this might be another thing you've heard of, or maybe even covered at GCSE. The critical angle is, let's say we were to take this substance here. In this case, I'm saying this is where n1 is greater than n2. So I'm speeding up as I come out, that's why I'm going away from the normal. Now you can see that if I were to increase theta 1, it's also going to increase theta 2 because of this this formula, they're directly proportional to each other, or the signs of them are directly proportional to each other. So if I increase theta 1, I'm increasing theta 2. Now, that means that I could technically increase theta 1 so much that theta 2 will become 90 and it will travel along this boundary. And that's exactly what the critical angle is. So the critical angle is the angle of incidence, so this theta 1, angle of incidence at which the refracted light travels along the boundary. Okay, so the refracted light is going to come out and it's going to look something like this. So we're going to have some medium here. We're going to have light coming in, and then eventually with this value of theta 1, let me just draw it a bit bigger so we can, we're going to call theta c. So that's our symbol for the critical angle, so theta c. This is going to come in, and our refracted light is just going to travel along this boundary here. So theta 2 is going to be 90 degrees, okay? And so what we can say is we know theta 2 is 90 degrees. So let's put that into this formula. So saying that we know n1 is just n1. Theta 1 we're now going to call theta c because this is the critical angle, when n2, and then we know sine of theta 2 is 90, so sine of 90 is 1, so we can just say that this is n2 times 1, which is just n2. And because of that, we can then say that sine of the critical angle is just going to be n2 over n1. This equation is also on your formula sheet. Now there is a condition that goes with this equation, and the condition is that n1 has to be greater than n2, meaning we have to go from a, so it must be from a higher optical density to lower optical density. Now, there are a few ways that you can prove that this condition is true. This condition is also on your formula sheet, so you don't have to memorize it either, but you do have to know it, because what we can say is if we were to look at it the other way around, so we've always took the examples of air and glass in this video, so let's continue with that. So if we have air on the top going into glass, it means we're traveling from a less dense to a more dense medium, and so the angle is coming down here. So as I increase this angle, I'm getting closer and closer to this going straight down, and that's not going to get anywhere near going along this boundary, okay, unless I put my initial angle going along the boundary. It will continue along there, okay, but this isn't what we're trying to get at, okay, so it's not possible for this to occur. It is possible in this case because we know it was going away from the normal, not towards the normal. The other way you can explain it, so this is conceptually it doesn't really make sense, but also mathematically it doesn't make sense, because if we had n2 greater than n1, then this sine value would be greater than 1, and we know that can't happen. If you put the inverse sine of 2 into your calculator, you'll end up with a math error or a syntax error, one or the other, I can't remember which. I think it's a math error, and that's because sine can't be bigger than 1, okay? So the inverse sine of something can't be bigger than 1. Okay, so this can't be bigger than 1, which means n1 has to be bigger than n2, so this only happens when we're going from a less dense medium, a higher density medium to a lower optical density. You could then ask, if this is true, this theta c is specific to each boundary. Okay, so the boundary between air and glass will have one specific critical angle. The boundary between Water and oil will have a different one. Water and glass will have a different one. It was all dependent specifically on the refractive indices of the two things that you're traveling from and to. Okay, and again, applying this formula isn't too difficult, so I'm not going to go through any examples in this video. But what we could say is what happens if we continue to increase this angle, because it isn't the biggest angle we can go to. If we continue to increase this angle, what happens? And we know that we're going to continue going away from the normal, and so if we increase theta, so it's greater than the critical angle, what we see is total internal reflection. Okay, and so this is going to be a separate video, but this is all we have to know about refraction up to this point. Hopefully this all makes sense, and thank you for watching.